Now we are going to see, we are going to have a letter, a hinge, then we involve in a pulley. So that's the case we are having in this lesson. But please don't forget to subscribe to the channel. Okay, a rod MB of length 0.6 meters and mass 10 kilograms is hinged at A, and its center of mass is 0.5 meters from A. It means that this is not a uniform rod because the center of mass is not in the middle. A light inextensible string attached at B passes over a smooth fixed pulley 0.8 meters above A and supports a mass M hanging freely. If the mass of 5 kilograms is attached at B so as to keep the rod in horizontal position, find the value of M, then the reaction at the hinge. So we start by sketching. Of course, you see the rod is going to be kept in horizontal position. So these are I start with that idea. So I have to keep it in horizontal position. So let me see. This is going to be my horizontal. This is my rod there. So this is going to be my A, and then here I'm going to be having B there. Now they are telling me that here at B they are attaching a 5 kilogram mass at B so as to keep it. So I have a 5 kilogram at B. So there I'm going to be having 5D, the mass times the gravity. Now they're telling me that a light inextensible string is attached at B and passes over a smooth fixed pulley 0.8 meters above A. So above A we have a pulley. So we have a pulley that says this is going to be our above A. So we have a string. Of course, this one is fixed. We have a pulley fixed there above A. So let us call that. That's going to be our pulley fixed. Okay, so it means that now this string is going to be attached at B and passes over that fixed pulley like that. Then it's 8 meters above. Of course, it's going to be carrying a mass, telling me that this mass M kilograms. M kilograms. Of course, it will exert a weight. That weight is going to be mg. Okay, so above, so here we are having this as 0.8 meters up here, up down here, like that. Okay, we are still analyzing the question. Of course, because this is a string, it's going to be having the question. Now, this one here is having a hinge there. So it means that now this string is trying to, because this weight is going to be pulling this down, so this string will be pulling it in the direction that it's in the horizontal position. So it means that now the direction of the tension is going to be in that order, so that it keeps this in a horizontal position. Okay, so they're telling us that. Okay, we are almost there. Then they're telling us that and its center of mass is 0.5 meters from A. So 0.5 meters from A. I think this is where our center of mass. So this is non-uniform. So 0.5. So from here up to here, we have 0.5 meters. And the whole road is 0.6. So the balance here is going to be 0.1 meter. So here, 0.5 meters from A, our weight is going to be there. But this one is 10 kilograms, so we get the mass times B. So basically, we are almost there. I think that's all we have for the diagram. Now, we have finished our diagram. We do this with ease. Nothing is going to take a lot of. Okay, so now we have basically that. So the question is, they want us to get the value of M. But now, because this is the same string, it's going to be having now. Because this one is going to be pulling, this is going to be pulling the string down, this is passing over, of course, our tension is going to be acting upwards there. Okay, so I don't know this angle, let me call this angle theta. Okay, let me adjust this distance so that I have to, let me adjust this distance. So we have our angle, theta there. This is going to be still 0.1 meters. Okay. So after having that, now of course you see, this one, if it's in equilibrium, it means that this one is going to be equal to that. And then we have also to resolve this vertically, and then, so resolving this vertically, you see that this one is going to be here. I'm going to be having t, then you see this one is adjacent, cos theta, then horizontally, upwards, vertically, we are going to be having t sine theta, resolving this tension in the spring. Now, because we have a reaction at the hinge, this is going to be our reaction. Now, where this is our reaction R, it means that now we are going to have a vertical component from R, which I'm going to call Ry. Then I'm going to have a vertical component, which I'm going to call Rx, with an angle alpha. Okay, we have used theta with an angle alpha to the vertical. As simple as that. So, why have I determined the direction of the component, the horizontal component of this? Because we say if the tension in the spring is coming this side, then this one is opposite to the direction of the tension in the spring, as you see. So the reaction, the horizontal component and the horizontal component of the spring, they will be having opposite direction to keep it balanced. Okay, so basically that's what we have. Then let us see the value of A. So part A, value of M. So to keep this particle in equilibrium, so in equilibrium, it means that now this T, the upward force, resolving the upward force T, is going to be equal to 2md. So now it means that we have to get tension first so that we can get our md. Okay, so now resolving, you see that now here we have many forces. This is our hinge, we have Rx, we have Ry, we have also T. So we have a lot of forces. Always, by the way, in most cases we take moments at the hinge. Why? Because at the hinge there are many forces. We take moments where we have many forces. So you see that I want to get T. So you see this one is acting anti-clockwise. So I'm going to take moments at A anti-clockwise. Okay. So you say the sum of moments anti-clockwise is equal to the sum of moments clockwise. So anti-clockwise, I think we can start this T here is going to be acting anti-clockwise. So all of T sine theta, then time. The molecular distance from here up to here. I think this is from here up to here is the length of the aurory, which is 0.6. Now, all more forces coming out from area taking moments from, their moments are going to be 0. Why? Because if you are coming from A, the perpendicular distance from A is 0. Because at A, the distance you've moved is 0. So that's why the force is there, but there's no perpendicular distance. That's why this one is going to be, this one is going to be 0. Even this, and you see that also this one, T cos theta, is coming to A, even its moment is going to be 0. So the only force surviving is this one, and this one. Those are the only forces surviving. Okay, so it will be equal to 10d, then times from here up to here, so that from here up to here is 0.5. Then plus these ones for them, they are acting clockwise from A, I think you see. 5d, then times from here up to here, we have 0.6. Now the question is, how are we going to get our this theta here? Now, if you look at that, I think you can see that if I have this is going to be my B, this is going to be my A, this is going to be the, so here is 0.8 meters, and from here we have 0.6 meters. You see, when you square this plus the square of this, you shall be getting this as 1 meter using Pythagoras. So, meaning from here, my T times sine theta. From here, if this is my theta, I have the opposite 0.8 over hypotenuse is 1. 0.6 will be equal to 10 times 9.8 times 0.5 plus 5 times 9.8 times 0.6. So from here, give us our t. Don't show us this. You just give the t. Okay. That's the answer I'm getting. Then I convert to a fraction. You see that it's going to be, so it's going to be 490 over 3 newtons. That's going to be my tension. So after getting the tension, now I can come and I get this. So my mg equaling to t. So it means that now my m is going to be 4980 divided by 3, then divided by 9.8. These are going to be, okay, my m now is going to be so here I'm going to get T 50 over 3 newtons. So that's going to be I mass m. You can handle it the way you want. If you want to give it to 4, you give it for the small presses, even this for the small presses. Okay, so we have the mass they wanted us to get. So now let us take the reactionary heat. Remember, so they are asking you reactionary heat, dissolve horizontally, dissolve vertically, as simple as that. So it's always easier to dissolve first horizontally because there we get our Rx to be easy. So dissolving horizontally, we have this Rx. Is it the one horizontal force? Then this one also equaling to T cos theta. So my Rx is going to be my T, which is 4,9 over 3. Then times cos theta. From here is cos theta. It's going to be adjacent 0.6 over 1. So my Rx from there, you see it's going to be 490 times 0.6. I'm getting 9.8 newtons. So that's my, as simple as that. So now we can also resolve. Now after that we resolve vertically. Okay, we resolve vertically so that we can get the horizontal component. I mean the vertical component. So vertically, so we have R, Y, those which are going up. We also have this plus T sine theta. Those are the only, I think. No. Plus this T, I think you see that also. So plus T, you see it's going up. Then it's going to be equaling to, we have 10 plus 5G, then plus mg. So plus our mg. So from here you can see that this is 15. So my ry is going to be, this is 15. So we have 15G, then plus our m, which is 50 over 3G, then minus. From here is that our t is common. Okay, let me, because t is common. My t is common, so I factorize out t. I'll be adding now sine theta plus 1. So my ry is going to be 10 times 9.8 plus 50 over 3 times 9.8, then minus. Okay. So my t, which is 490 over 3 into sine theta, you see it's opposite, 0.8 over 1 plus 1. So my ry, now you give us the answer. Okay. Let me pause and I calculate. I think you can see my answer there. Okay, which when I write it as a fraction, it's going to be 49 over 3. So it is going to be 49 over 3. So that's now my horizontal component. So when you come to our sketch there, you see this is our ry, this is our rx, This is going to be our, then we set our R, set that there. So, meaning that our R is going to be the square root of this squared 9 to 8 squared plus 9 over 3 squared. So our R from there is going to be getting 99.351 Newton. So that's my R there. Then the reaction at the end. If they wanted us to get the direction, then we would have also got the direction. So our theta there would have been tan inverse of, this is going to be the opposite, which is Rx, which would be 98 over 49 divided by 3. And you see you are going to be having 2 over 3. Okay, shift time. So here our theta would be 80.54 degrees. See that this one was going to be 2 divided by a third, which is should call B6. So 2 times 3, which is 6, then tan inverse of that is that. So that's how we handle that. I think now we have seen also the ladder evolving there, and also pulley. So that's it. I wish you the best. Don't forget to subscribe to the channel. This is the alpha, not theta. It's alpha we set here, so it's alpha. Let's correct that.